So, all right, let's go back to the formula for conditional probability and introduce another very important concept in probability, and that is the multiplicative law. And remember, we said that the P of A is greater than 0, so multiply both sides of the formula for the conditional probability by P of A, and you've got it out there. That is called the multiplicative law. So the multiplicative law is the probability that A and B happen. You can break that down by saying, all right, that's like the probability of A. Let's look at A first. Probability that A happened first. Then, do I need the probability that B happened? No. More properly, I need the probability of B given that A has happened. So that's how these things evolve. Note, by the way, that there's nothing special about A, nothing special about B. The whole thing is symmetric in A and B. So I could either use probability of B given A or the probability of A given B to do the multiplicative law. So I could do either A first or B first. Okay, so what does this lead us to? It leads us to a very, very, very fundamental and very important concept that we use repeatedly in probability, in statistics, in epidemiology. All right, and that is the idea of independence. So we say that two events A and B are independent if the probability that A and B happened is the probability of A times the probability of B. Now, remember, the conditional probability formula was that, and it said the probability of A given B is this. So what is when we compare these two, that tells us that we have an independence implies that P of B given A is the same as P of B. And since there's nothing special about A and B, it also means this. All right? So what this is telling us is that knowing that A has happened is not going to change our mind about whether B will happen or not. Knowing that B has happened is not going to change our minds about whether A is going to happen or not. They are independent of each other. Okay. This is what we use repeatedly when we build up our knowledge by taking more and more and more patients. It will be very difficult if taking the second patient is going to change what happened to the first patient and so on. So very often we model events as independent of each other. Namely, what happened to the first patient is going to be independent of what happens to the second patient, independent of what happens to the third patient, and so on. So that's with people. It's a little bit more difficult to comprehend. I mean, we can think about it for a roulette table or something, when you spin the ball around, and what happened half an hour ago is not going to have any impact on where the ball lands up now. Okay, but it takes a little bit of thinking about whether we have independent events or not. But we make this assumption quite often. It needs to be justified, but we make it quite often, and it's extremely useful. Here's one example of this, and that's to do with Mendelian segregation. And if we have a heterozygous sperm fertilizing a heterozygous egg, then the first part of Mendelian segregation tells us that it's equally likely to take the dominant as the little a from the sperm, and it's equally likely to impregnate the big A or the little a from the egg. Okay, so we would say probability of half, half, probability of half, half. Step 2 is that you have independence. So whether this couples with that is independent of whether it couples with this. So the result is that you would get this AA a quarter of the time. Same thing here, you would get the A, little a quarter of the time, cap A, little a quarter of the time, and little a from both a quarter of the time. And secondly, there's no difference between this and this. It doesn't matter where it came from, so that combining these 4 terms together, we get that we should get from a mating of heterozygous pairs, we should get dominant-dominant a quarter of the time, recessive-recessive a quarter of the time, and heterozygous half the time. And indeed, this is what we seem to see with thalassemia, or as they used to call it, Mediterranean anemia. Although it's not quite fair to call it that, but this is basically what happens when you have an unaffected but carrier father with an unaffected but carrier mother. It's a little deceptive because all the offspring are male, but they don't have to be, of course. You can have any mixture you want in there.